Subchapter 6.3 Diesel Cycle, the ideal cycle for compression ignition engine. Diesel cycle is also known as compression ignition cycle or CI. During the compression stroke, only air will be compressed. And instead of having spark plug for ignition, diesel will be injected to the compressed air at the end of compression when piston reach top dead center, and the reaction will create combustion and drive the piston downwards. Thus, in this combustion process, it is similarly to constant pressure heat addition. The diesel cycle is designed to operate at much higher compression ratios than the spark ignition engines. The typical values for the compression ratios is between 12 to 24. By applying the standard air cycle assumptions, the ideal diesel cycle can be represented such as shown in this diagram. Process 1 to 2 is the compression stroke, where the pressure and temperature will rise. Once the compression stroke ends, there will be constant pressure heat addition to the system as the process 2 to 3. For the process 3 to 4, the gas will then further expand and pushing the piston to the bottom dead center, where the volume is maximum and reducing the pressure. And process 4 to 1 is assumed to be heat rejection in constant pressure to the initial condition of the cycle. With respect to this example, the compression ratio is given by RV is equal to V1 over V2 during the compression stroke. And the cutoff ratio is the ratio of the volume during the constant pressure heat addition process and is given by RC is equal to V3 divided with V2. There are 4 processes involved in diesel cycle. Process 1 to 2 is isentropic compression process. Process 2 to 3 is constant pressure heat addition process. Process 3 to 4 is isentropic expansion process. And process 4 to 1 is constant volume heat rejection process. For process 1 to 2 and 3 to 4, we can use isentropic relation to find our related properties. Again, there are no work involved in diesel cycle. We only have heat transfer in at the process 2 to 3 and heat transfer out at the process 4 to 1. For constant pressure heat addition process 2 to 3, from the non-flow energy equation for isobaric process, we can obtain this expression. And we can get this equation to find the heat transfer in. For the constant volume heat rejection process 4 to 1, we can have this expression from the non-flow energy equation. In addition, we can use the ideal gas relation for process 2 to 3 and 4 to 1, where for constant pressure heat addition, we can use the relation of V2 over T2 is equal to V3 over T3. And for the constant volume heat rejection process, we can use the relation of P4 over T4 is equal to P1 over T1. For the thermal efficiency, it is given by this equation. We can derive the thermal efficiency formula to have this expression. This will be the derivation for your perusal. And lastly, the advantages of diesel engines are higher thermal efficiency, lower fuel costs, more suitable for applications that requires large amount of power such as buses, lorries, trucks, locomotives, and emergency power generation set.